Hello everyone, my name is Aaron. I'm very happy to be here today to present my work. That's about how to do quantization on graph neural networks with AutoML. And this is a joint piece of work with many colleagues at the University of Cambridge. And I have a shared equal contribution with Mr. Do Wang. So as we all know, GNNs today are getting really popular in different domains. This includes, but not limited to, recommendation systems, scientific computing, and also point cloud processing. And it is interesting to see how GNNs are being operated on very different hardware systems. For example, in recommendation system, it's very popular to operate GNN on cloud platforms. And in scientific computing, we've seen applications of how to use GNNs to discover new drugs or new antibiotics. And some of those applications are running as supercomputers. And on point cloud processing, after the LiDAR capture the data, it's very likely that GNNs will be running on edge devices. Given that GNNs are now a popular workload on different hardware systems, we're interested in finding a way to help GNNs to perform more efficiently on these systems. And a very obvious answer to this is quantization, where we shrink not only the data formats, but also reduce the computation complexity. So we're interested in finding an efficient quantization strategy, but how do we find it automatically? And the immediate challenge we have is so even if we forget about the quantization, the GNN network architecture can vary a lot on different data sets. And so this implies that we have really large design space of the GNN architecture. This means we can choose different hidden units, different activation functions, different aggregation methods, or different attention methods. And in the graphical illustration here, I'm giving an example of how we define a graph neural network. Is that we have a couple of graph neural network layers that in our case we call them graph block, and each graph block can have 4 smaller sub-blocks that are linear, attention, aggregation, and activation. I will revisit this design space later, but just keeping in mind that this is a more involved and a larger design space compared to convolutional neural network, where you only have a single convolutional layer. And what happens is that when we consider the quantization now, we suddenly have an even larger space if we allow mixed quantization, because each of those sub-blocks can be quantized differently. And also what happens is that quantizing them differently might imply the interaction with the architectural space. So here we propose to use NAS to automatically discover the optimal architecture quantization pair for a targeting data set. Previous approaches mostly consider previous NAS approaches on GNNs, mostly reinforcement learning based, so that they are very computationally expensive. Because each action step of this reinforcement learning will require certain convergence information from this underlying model. So this normally implies a high search time, a very large search time. And what happens in previous methods is that they normally only consider what we call a microarchitecture search space. That is the size of those hidden sizes or the activation types. But they do not really consider the macro architecture space. For example, how graph blocks should actually be considered, should actually be connected, and also how those graph blocks should be shortcutting each other. Also, obviously, previous methods do not really consider the quantization search space at all. So, as we mentioned, for each graph block, we can divide them into 4 smaller sub-blocks. Mathematically speaking, that's the equation 1 that we're showing here. The details of this is in our paper. And we're in our research, we're really allowing a very flexible quantization strategy. As illustrated in equation 2, we allow different subblocks to have different quantization strategies, and we allow weights and activations to have different quantization strategies as well. So we're really relaxing the quantization search space here. So our NAS method, what we call is low precision graph NAS or LPG NAS. It's based on a recently published paper called Differentiable Architecture Search. It's similar in a way that they are all gradient-based NAS methods. So the key idea of it is that each part of the model is including the quantization options now has a number of candidate components to be selected. And we use those validation data set to train a controller to pick from those components. At the same time, we use the training data to train the parameters of these components that have been picked. And in our case, to enable quantization, to enable search on quantization, the goal of our optimization, the additional goal of our optimization is to push the model to be smaller, right? Or push the model to have smaller computational complexity. What happens in reality is that we push the model to use smaller bit widths. So for each choice of the architecture, we now multiply its cost with the probability of that choice being picked. So this is equation 3 that we're presenting here. What I'm showing here is really the quantization loss, and the details of how to design this loss is also in our paper. So to give you a graphical illustration of what's happening, the blue blocks are the controllers. We'll have a architecture controller that is outputting PA. So this is the probability of each architectures. And this PA is populated to each graph block as expected. And for each graph block, we have those 4 small sub blocks that I've mentioned before. And the architecture controller is in charge of picking a suitable architecture option from each sub block. And also, in the same time, we have this quantization controller outputting PQ. This PQ goes to not only the sub blocks to pick the suitable quantization strategy, but it also goes to the router. So the router is a component that we've designed to manage how shortcut connections should be placed across different graph blocks. For example, the router may choose to shortcut between graph block 0 and graph block 3, and this is purely determined by our search mechanism. In the microarchitecture search space, if we break it down, what we really have is for the Lth layer, what we'll have is a feature transformation operation. This is basically a linear layer or a hidden layer, whatever you call in machine learning. What happens is we also gather information from the neighboring nodes of a graph, and we use attention parameters to message to re-weight those messages passed from the neighboring nodes. And those attention mechanisms are also searchable components. And then we will have to have an aggregation and also a combination. This means how do you combine those aggregated messages? This can whether be a maximization or you taking the mean of all those collected information. So this is also a searchable component. At the end, we have, of course, the searchable nonlinear transformation, which is the activation function. So this is just to give you a graphical illustration of how this PA is passed to different sub-blocks that I've just mentioned before. And how does the controller actually produce those information, and what is actually a controller? So in our case, the controller is a learnable embedding that it's connected with a bunch of fully connected layers. The output of this controller, we view that as a probability. So we take the softmax of the output to make it a concrete probability that's lying inside the 0 to 1 region. What happens is the candidate operation with the highest probability is picked, and after it's picked, we train the operator with its weights, right? So to update the picked architecture, basically. And the quantization controller basically follows the same logic, and the details of those two controller designs are in our paper as well. What's interesting is we also have this thing called macro architecture search. What happens is now we have a router that's controlling how shortcut connections should be placed, and each shortcut connection now has a gating parameter G. And we use Gumball softmax with a temperature tau to control the randomness during the training procedure. We find this quite important because at the start, you want that to be a random exploration, but then it should slowly gain knowledge, and the randomness should decrease when the training proceeds, right? And the details of this design is also in our paper. So to give you an idea of what this have achieved, what LPGNOS has achieved, we're only showing the citation data set here because of time limitation. A lot more data sets are in the appendix in our paper. So it achieved around 1000x decrease in search time when compared to a brute force quantization tuning. That's basically a guy that's trying quantization options one by one. And on this transductive learning setup on the citation dataset, we see an improved accuracy when the model size is similar to manually designed networks. To make it more visually pleasant, we show that our methods actually show a better Pareto frontier compared to on different model size budgets and buffer size budgets. So for buffer size budgets, what we're referring to is the maximum activation size that the model might utilize on a device. So we basically show that the LPGNOS can achieve a better frontier when compared to both manually designed and searched networks on different size budgets. And this is the end of my presentation. If you are interested and if you are looking for more details, please look at our paper. Thank you.